Okay.
An hour and 15 minutes actually in this room.
Okay, so we should be good. This is work that I've done together with my students, most and foremost Yaji Miao, who graduated this summer, and I guess many of you know him, but also with visiting student Abhinav Gupta and another CMU student, Leonardo Neves. So what I'm going to talk about today is audiovisual features for context-aware speech recognition. I want to start by introducing a method for doing speaker adaptive training for deep neural networks by adding additive feature shifts to the input features, which is the method that we're using or abusing to also not only do eye vector adaptation, but adapt the speech recognizer to the speaker microphone distance in recognition of videos, and that we're then extending to also add those visual features in. So we're using one method to do speaker adaptation using eye vectors, then speaker microphone distance, and then visual features from videos. And at the end, I'll talk about adaptation also of the language model to with those same visual features. So automatic speech recognition, we all know the hidden Markov model-based approach. We all know hybrid speech recognition. We break down speech into a sequence of context-dependent subphonetic states, and we predict the likelihoods with deep neural networks. And of course, there is a lot of variability in the speech signal. There is language variability, there is a speaker identity, there is distance and channel, and then maybe even other variability that we don't know much about. And of course, and now I saw Najim just coming in just now. So here's the slide that you're gonna recognize, and that I hope you like. It's from Sajin's.
Still alive.
Yeah, it's from Sachin's thesis. There is a lot of variability, and the good thing is that the biggest variability is the phonetic variability. That's actually the signal that we want to recognize. But there's also variability in the speaker information. That's the dotted line here. Then the channel, that's the dashed dotted line here, or some error or some still unexplained residual variability. And even if we do things like capsular mean normalization, capsular variance normalization, there's still a lot of this unexplained variability. And maybe this visual speech recognition will be something that can help us reduce this variability a little bit more. The same plot, also stolen from Sachin's thesis, shows us that a lot of the variability, the phonetic variability, of course, is something that's only contained within sort of a window of 250 milliseconds, but all the other variability stays and is longer for 250 milliseconds. So the point that I'm trying to make is that anything that gives us information of a window that's longer than 250 milliseconds will probably be something that we can use to adapt the recognizer to and sort of compensate for this residual variability that is not phonetic variability, but something about channel or speaker. So we want to reduce this unwanted variability, and that's what we've been doing in speech recognition for a very long time, adapt our models in some way. For Gaussian mixture models, the mainstay of speech recognition, we've been doing speaker adaptive training, shifting the means of the Gaussians a little bit. And obviously, we want to do the same thing for deep neural network. It's sort of our instinct. If we have a new tool, let's try if all our other tools can work with the new tool. And throughout the talk, I'll sort of distinguish two cases, doing adaptation by saying, well, we're taking an existing model and just adapt it to the new conditions, to the test conditions. Or we can even, and that could be done by retraining the model a little bit and just adapting it, or by doing speaker adaptive training, or generally adaptive training, by training a model in a way that already incorporates extra information, which we then also have to extract for the test data. So there are two slightly different approaches, and what we are trying to do here is this adaptive training. Now, of course, there's been a lot of work, speaker adaptation with deep neural network models. It wasn't called deep learning at the time, but when neural networks were first used for speech recognition in the 80s, then people came up with per speaker models and the so-called MetaPi network already in 1990. So this is none of this is new, and we could have done it 25 years ago if only we'd had the computation and the data. People used discriminative input and output transformations for speaker adaptation. certain DNN layers became speaker dependent, or we're learning hidden unit contributions and use it for adaptation in a SAT approach. And even without changing the structure of the network itself, we started to adapt to perform feature-space SAT, which means we're not really changing the structure of the network, but we're trying to adapt the features in a way that we can use our model in that they fit better to our model. This is something that we've done with GMMs as well. And so in 2014 or 2013 and 2014, a lot of work appeared that did the speaker adaptive training using I-vectors as an input to the deep neural network. So there was Soltau, Hagen-Soltau and George Sohn in 2013, and immediately afterwards Google and Montreal discovered this, and I think they discovered it pretty much at the same time. So it was sort of an obvious idea to use I-vectors as additional inputs to a deep neural network and adapt the recognizer this way. A variant of that is to use certain speaker codes to adapt the deep neural network acoustic model. So what we're doing is taking essentially the same idea, but do the integration of those I-vectors into the deep neural network in a slightly different way that works better for us, and then take this idea and replace I-vectors with an estimate of the speaker microphone distance or visual features that we extract from the video. So let me first explain our approach to I-vector adaptation, performing feature space SAT for deep neural networks. So the standard approach in the I-vector adaptation, I-vector speaker adaptive training of DNNs is to take our general speaker independent DNN, take the speech features and simply append the I-vectors to the speech features. And so we just have a bigger feature space. Some of the features change every frame. Some of the features do not change every frame. They're the I-vectors that we extract for the speaker, or at least for the utterance. And what we said, well, we had a database, the Babel data, where this didn't really work well because we didn't have enough data to extract I-vectors reliably. So what we said, well, can we train a little adaptation network that takes the I-vectors and learns to predict a lower dimensional, just a little feature shift, just an additive shift to the input features, which we can then use to reduce the model, to improve the model, rather than appending the features directly. So we tried this idea, and it works really nicely. So instead of appending the I-vectors to the features, we're training a little adaptation network, and that takes I-vectors as input, constant for the whole speaker, and predicts a feature shift to the input features of the network that we can then apply to the features during training. So it's a two-step process. We first train a speaker-independent DNN, then we take the speaker-independent DNN, backpropagate the training data through the speaker-independent DNN, and update a little adaptation network with the deltas to the original speech features here. So at the time when we developed it, we didn't know it, but it's the same idea that is now very popular in those ResNets, where you take many small networks and you sort of train another network on the residual that you're seeing on your inputs of your network, and try and produce and reduce those residuals over time. So it's a very similar idea that we're doing here, simply taking the residual error at the input features and train a small network to reduce this error a little bit further. Train the speaker-independent DNN, train the adaptation network, and then train or fine-tune the speaker-independent network a little bit more. It's all standard backpropagation, and it works quite well. So we can, of course, at this time, make this into a general framework. We are not using anything specific about the I-vectors, and during decoding it works nicely as well. The good thing is we can extend it very easily. It also works, for example, for bottleneck features, or it works for convolutional neural networks. And so I'm going to present numbers on this. We started our experiments on the TED-LEUM database. We're using a standard DNN recipe for training an acoustic model on that. It was trained using CALDI and PDNN. And we tested them on the IWSLT test set, the DEF 2010 and TEST 2010 test sets, a 4-hour test set roundabout. And sort of evaluation systems have a baseline word error rate of about 16% on this task. And our system gives us round about the same performance. So a standard BMMI, GMM gives you 24% word error rate. Our DNN baseline, plain, unadapted, give us a word error rate of 20%. And if we do this SAT DNN technique on its own, we're getting a word error rate of 17.3%. So that's a 13% reduction. If we do it on bottleneck features as a baseline, we get a word error rate of 17.7%. And if we apply the SAT I-vector adaptation technique, we're going down to a word error rate of 16.2%. Gives us another 8% word error rate reduction. If we do it with convolutional neural networks, we start out with 18%, and we get a word error rate of 16.8%, a 7% reduction. So this technique gives us exactly the same improvement that other tuned evaluation systems on this task are giving. So it's a very competitive technique to include I-vectors in DNN acoustic modeling, and it gives gains in addition to other techniques like bottleneck features or convolutional neural networks. Oh, sorry, yes. No, please.
So this might be a question. So can I think of the I-vectors as sort of like an embedding of each speaker?
Yes.
And did you talk into the I-vectors? Like, did you update them?
No. So the
Okay, so and then my related question was, what if you just randomly initialize, instead of using I-vectors, you use the random vectors of that, but learn it.
So I mean, the person to ask this question would be here, I guess.
Well, actually surprised me that I know that the guy from IBM, what he did, he trained a DNN with an I-vectors on it, and after that, he said when he tested, he just put 0 in the I-vectors, and he only get the same gain. Yes. Well, not same gain, but almost close a gap between, yeah. So if you create, yes, he trained it when he tested in the dev. He only put 0 in the I-vectors, and the system still behaved very good compared to the baseline.
Oh, so was this George or Hagen saying that, or
The IBM.
George Thorne?
Source node, yes.
Oh, really?
Yeah, he told me that when we were, yeah. He told me that he trained the I-vectors, he would say when he did it, that when he tested in the dev, he just put 0. He don't estimate the I-vectors. And he still give you better result than the baseline.
Interesting, because I mean, we tried the same technique, and our finding was that the I-vector extraction is a bit finicky, and on some databases it worked nicely. On some databases, the I-vectors seem to be unreliable, and particularly on the test data was pretty. It wasn't easy to get improvements. Interesting.
So that's what he told me personally, and also the fact that if you do an I-vector in insurance based, so the measure of the full variability there is not the speaker, so it's the phoneme you said it. So it's more like a trans adaptation, it's not like a real speaker adaptation. If you do use it with the whole recording, yes. If you want to do small and only reference, it's more the phoneme variability that you capture with the average.
Right. Right. So one of the experiments that we did with this was that because you're not feeding in the I-vector, maybe that's a good point. So one of the advantages of this method that we found was that it works better on shorter amounts of data, and the explanation of that, of course, is that we extract the I-vectors and we're averaging it, and we input a constant feature into the recognizer rather than the I-vectors. Okay.
Confusing question. If you could go back a couple of slides to the picture where this one's good. So if I look at the upper picture, could I think of this particular method of adapting as saying, normally when you backpropagate from the right side, you're adjusting all your network layer weights to try and improve the liquid function, but normally when you come to your input X, you stop because you can't change the input.
Right.
But this is like saying, what if I could change the input? So you're actually backpropagating through the inputs. saying,
Yeah.
how could the input be changed? And then the rest of the green stuff is just telling you how to change the input. But of course, you need to do it based on some longer range characteristics of the input, and that's your I vector.
Yep. Yeah.
So for example, the poor man version would be, forget about all the green stuff, just compute the capsule means, apply a minus sign to it and stick it in there. And you'll be doing capsule means.
And you could, the same structure could do capsule mean normalization, and yeah, that's.
So in that case, do you are your X without capsule mean normalization, or do you still do?
No, we still do capsule mean.
In principle, you would have done without it, and maybe the I vector would find out.
I mean, I guess it's some. Carl came up with the sequence summarizing network idea. That was my thought when I read about this. I said, oh, so you're learning some property of the whole recording and subtracting it. That would be structurally it's the same as this one, but it would do the same. What you're trying to subtract, your intuitive explanation of what you're trying to subtract would be capsule means, and so yeah. So
This is, of course, nonlinear, so it could be more easy.
right. But when I read about those, the motivation behind why do those ResNets work, when you take the inputs, you take a network, and you bypass the network and again provide the original input at some intermediate stage, and then train again and backpropagate the errors so that a really deep network has access to the original features at every intermediate step, then it becomes sort of a similar idea to say, oh, I'm not trying to train a full network, but I'm training something that still sees the original features and tries to gradually reduce the original features, or gradually shift the original features towards becoming something that's more easily trainable. And that's sort of what we're doing here, but not at 50 steps, but only at one step.
Only to follow all these techniques assume that you have some significant algorithmic delay. You basically look ahead a lot over the sentence or something over quite a long time. So all these techniques are not real time. Does it bother anybody?
At this point, it doesn't bother us. I mean, all these are batch experiments.
Yeah.
I think you can, for capsule mean normalization, you can do online estimation and online updates for the speaker microphone distance that I'm going to talk about next. We're even making it dynamic, so it's time dependent.
So you say you can do it on the past data, on some small amount of the past data, or small amount of the future, and still it's going to work?
We haven't done the experiment with the I vector extraction. It might be a little bit tricky to.
Oh, I don't mean it as a criticism. I just
No.
want to make sure that I understand what are the assumptions.
Some of the things we're doing, we have something like a 1 second look ahead, or you can think of it as a 1 second later.
Sure,
You don't have to look.
yeah, that's fine. That may be fine. That's something you may be willing to live with. Yeah, I
So you
understand.
can limit a small latency rather than go with
Yeah, I think converting it from a batch step into a reasonable latency online capable process is typically reasonable and typically works well.
They summarize, but it's
Right. The nice thing about the I vectors in particular is that you can extract them without supervision. So it's not like you have to decode once, adapt, and decode again.
I know. Well, yeah, but it's still.
Yeah, you need a reasonable amount of data. And
Since Dan probably is not here, I'm the other Dan, Daniel. Calvi has online decoding with iVectors. It just looks at the past and gives you an online adaptation with some latency. It's a streaming iVector extractor. So it's in Calvi.
So you hope that your future is similar to past or something.
We're always hoping that there's some stationarity.
okay, I don't want to spend too much time on this. I just want to introduce the method that we're using. But yes, there's more questions.
You can use different number of layers for
So we're using a relatively simple adaptation network. I think I have the 3 layers, 512 neurons for the adaptation network. But we did a reasonable effort of optimizing it, but we didn't completely... So, okay, here's our comparison on the switchboard data. This is the DNN baseline by itself, no I-vector adaptation. This is the IBM method of simply attaching the I-vectors to the input features, and this is our method when we're doing this little adaptation network, and we find that this method performs at least as well as simply attaching the I-vectors to the input features, in particular in situations when you either have relatively few speakers or a small amount of data per speaker to estimate the I-vectors. So it's per se, it's not a dramatic difference, but for us it performs better and more robustly than simply appending the I-vectors. Okay, so this is the method that we're going to use, and of course what we're going to do is instead of using I-vectors for adaptation, we're going to use those visual features that we're going to extract from our data. So let me shift gears a little bit and talk about the data, the multimedia data. We started this work when we were working on the IARPA Aladdin project, where the goal is to take a video, extract visual features like there's water, there's a person, there's a fish, and ultimately the goal is we don't want to transcribe it, we want to generate a textual summary of what's in the video. So a man is fishing at a lake on January 9, 2009. So this date we get from the metadata that there is a person near the water and that he's fishing a big lake trout that weighs about 8 or 9 pounds. This is the information that we're trying to get from the audio, and indeed here.
Well, not one big lake trout.
So we want to recognize that it's a lake trout from the audio and put it into this summary. So we need to do some sort of speech recognition, but then of course there's a whole lot of generating this text, and then I'm not going to go into this. This is not the actual example of the project. This is a fake example. So don't believe that CMU or anybody is capable of doing this fully automatically. But we have this corpus. We have 8,000 hours of it. Only a third of it contains useful speech. Segmentation is a huge problem. Non-speech sounds are also interesting, and retrieval is the ultimate goal. So when we started to do speech recognition experiments, we said, well, we need something that's more reasonable. So we need to do something that contains more speech. So we collected a corpus of how-to videos, 400 hours of data that we scraped from the internet, people recording themselves, doing things and explaining to other people of how they do things and the advantages. It's still amateur instructional videos, so it's pretty challenging quality, but it's all in English, and it's all it contains lots of speech rather than having 2 seconds of speech out of a 2-minute video. Still, the speakers move around a lot, they hold the device differently, there's cuts in the video, and they're explaining things like how to change the oil in your car, how to make a sandwich, how to play certain ball games. It's still a very challenging corpus. So we did, the first thing we did is, of course, we're going to compare I-vector adaptation, but we're also trying to exchange, to look at the speaker microphone distance and say, can we use this approach to also learn, is this a close speaker, is this a far speaker to the microphone, and can we extract this information from the image or from the audio and feed it into the recognizer. So instead of, we're going to use the same basic approach. Here's our DNN acoustic model, but instead of extracting I-vectors from the signal, we're going to extract something that tells us how far is the speaker from the microphone and feed this information into the system. So how can we do that? Well, of course, we can use another deep neural network. We can take the ICSI meeting corpus that has 70 hours of speech recorded with 6 different microphones at different speakers, different distances from the speaker, and we can feed all the data in the system, and we can train a classifier that says, well, this is this channel, this is this channel, this is this recording, this is this recording. So we have 2,300 different recordings that are all different distances from the speaker. So we can train a bottleneck system on this data to predict which recording it is. And at the bottleneck layer here, we'll get an embedding that tells us, is this a close speaker to the microphone, is this a far speaker to the microphone?
How big are these vectors typically, like here, this bottleneck?
So here we're going to make them 100 dimensional so that they're consistent with the I vector and that they're consistent with the other features.
Actually, that's one piece which I was missing. You always try to get this dimensionality the same as the input vector.
Yeah, pretty much.
And you essentially really add things, literally, like sort of, you take the features and you add another vector.
Oh, so the input information to the adaptation network is always 100 dimensional, because that's the dimensionality of the I vectors, and the output dimensionality of the adaptation network is 440, and that happens to be the 40 logmail frequencies plus plus minus 5, so we have 11 frames context. Sorry, yes, I should. The last bit is always additive, yeah. Yeah, I need to put all these things into the next iteration of the talk, so this is very useful. Thank you.
Are you removing the temporal? Is the output a sequence of embeddings or a summary of it?
So at this point, it's a summary of it. It's constant, but because now we're doing, we're going to make it time dependent for the speaker microphone distance, because we know that this varies. A lot.
How is it summarized? Is it like an average?
Yeah, the network only predicts the target of the network is always okay. So the training target for the network is always constant. Of course, now that we're feeding time varying information in it, this embedding will be time varying as well. But when we do the I vectors is already a single number for every speaker, so that's already a constant information.
So in an ideal world, if there are n channels, that layer would learn exactly n points in any dimensional space, not very for everything else.
Right. Yeah. Well, but it wouldn't learn. What we wanted is not to learn the individual channel, but learn the characteristics of those channels and say, oh, those channels are similar to each other, those channels are similar to each other. Okay, so when we do those speaker microphone distance descriptors, we know that this is a time varying signal. So of course, rather than simply training a simple feed forward network, we might want to use temporal information, so the adaptation network can also be LSTM network. So it makes sense to use an LSTM network here because we know we have time-varying inputs and we have constant outputs. So we want the network to look at the temporal dependencies. So that's what we're going to do. And now we do have on our YouTube or on our how-to database, we have in total we have 360 hours. 90 hours of it so far we've been using for acoustic model training because it's been cleaned up and everything. We have a 4-hour test set. So if we train a BMMI GMM baseline system, we get 26% word error rate. If we simply run the recognition, we get 23% word error rate with a DNN. So if we do a simple DNN, we get a word error rate of 23%. And now if we do the adaptation with our distance measure that we extract from this bottleneck layer from the system trained on the ICSI corpus, if we simply concatenate it, we get a word error rate of 22.1%. And if we simply concatenate it and we concatenate the features extracted from the LSTM network, we get 21.8%. And if we do the adaptation method again, we're getting a word error rate of 21.5%. So adding distance information that we extracted using a neural network gives us, 2% absolute gain. And again, adding it using a separate adaptation network is better than simply concatenating it and doing a extraction of those features with a recurrent network rather than a feed-forward network is also slightly better. So we're doing some transfer learning from the ICSI meeting corpus, where we have many different speaker-microphone distances, to this corpus, where we also know that the speaker come close to the microphone, the speakers are far from the microphone, and that's a nice improvement.
How many hours did this exit?
It's 70 hours of recording, but the number of channels is slightly variable between each recording, so the total audio is 400 hours, I think, roundabout.
Also use the list microphone data.
Right, so there is some parts, NIST, CMU, but when it all adds only a little bit to the ICSI corpus, so we just went with the ICSI corpus.
Sorry, let me ask you a question to which there may not be a good answer. So what happens with the data you have now is that the bottleneck layer that is supposed to learn the channel characteristics, microphone, we call it, it has this special training data where the exact same speech has been recorded by different microphones. And so when you're presenting it, examples as in a particular channel as the target, it is getting, let's call it the same example, meaning it's the same speech recorded in different microphones and the target is changing. How well or how much worse do you think it would be if I simply had 6 recordings from 6 different microphones, but not of the same speech?
Yeah.
So this is ideal data, but is it really needed?
I don't think it is. I mean, we're training a very small model with a lot of data, so I could imagine that subsampling the data and saying, oh, I'm taking the first 5 minutes from this microphone, the next 5 minutes from this microphone, the next 5 minutes from this microphone, it probably...
Because what I'm thinking is, realistically, that's more likely to be the kind of data you can get if you know that there are maybe 10 different types of microphones in use. It's unlikely you'll get simultaneous recordings. Like think of some, you get users with handsets, but not something to be
Right. Well, to be honest, I mean, I don't even know that this really extracts speaker microphone distance.
Probably just extract.
Yeah, this is very interesting. You're essentially proposing to design a microphone classifier.
A channel classifier with more general.
It's more of a microphone in the back.
That's what I said, a channel. That's how we call it. Environment microphone code. Everything other than the linguistic one.
Right, and I mean, that's exactly why I'm telling you all this. I want to say that, well, really we don't know what we're extracting. We're extracting something that's related to the speech, and we feed it in, and now the question becomes, what else can we, why don't we feed in the visual features, and would this help as well? You had one more question, or?
I have some question on it.
Okay. So we said, okay, well, we have this thing that describes the acoustics. We feed it in, it helps. And so we did some analysis to say, well, does this actually correlate to the speaker microphone distance, or can we see that on those recordings where we measure that this feature has a great variability, we're also improving the word error rate? And indeed, that seems to be the case on those recordings that we don't, where we're not observing a word error rate improvement. The average speaker microphone distance variability, so the change in this input feature, is also very small. So it seems that on those recordings where we can detect a variability in the input feature in the speaker microphone distance, that's also the ones where we're improving. So it does seem to be the case that the network does something useful to help us adapt to the speaker microphone distance. Now, of course, the question is, why don't we just do I-vector adaptation on this data as well. And so, of course, we compared it. And the interesting thing as well, this speaker microphone distance adaptation gives us slightly bigger gains than plain I-vector adaptation. And if we take them both together, we get a small additional gain. And our explanation is that on average, we have very little data, or not enough data to estimate those I-vectors reliably because it's very dynamic. It changes very quickly. And so by doing this, performing a global I-vector estimation and then sort of this local speaker microphone distance adaptation, that gives us small gains, even though they're not really additive here. But the story is that this technique performs at least as well as sort of I-vector adaptation, which we use as a baseline for adaptation. So we're training the network to predict the channel, and we're just using the embedding at every frame. And we looked at the trajectories, and of course it does fluctuate a bit, but it gives us reasonably looking trajectories to say where is the speaker, is he close? And we looked at the variability of this, and the adaptation helped most for those utterances where the distance from the speaker to the microphone tended to vary the most within one utterance. So we didn't measure how much the speaker moved around in the video. I think LP is going to tell you that he can do that by looking at the videos. We didn't do that, but we wanted some measure to see are we improving on those videos where the person is moving around or not. Okay, so
So from a signal processing point of view, you are adding a term in the log domain, so it seems to be addressing like convolutional kind of noises.
No, we're doing this linearly in the feature domain.
I thought the features were log.
Oh, from the, okay, yeah. Yeah.
So you're adding so it's like convolution in the time domain.
Right.
Have you tried other kind of like adaptations that are not, for example, if there's noise?
Yeah.
It would not be an additive term in the log domain.
Right. We have not done that. We also tried it on MFCC features, but they're of course also right. We have not done it directly on the signal or on the spectral feature. We just say whatever it is, the network will learn it. But
essentially, what you are deriving in every case is some kind of summary of which is then eventually additive, right? So this is the definition of the adaptation. So, of course, you are right. It ends up at convolution in the signal domain. This is the way all this additional information is being derived. You are asking for additive things, right? Yeah.
Right.
But it's interesting. I know. I was thinking the same.
But I think the answer is we don't know what these features really are, and the way we are incorporating it isn't correct in a signal processing way, but still it helps. So why don't we feed in other things? And
I didn't say it wasn't correct. It's just
no.
one type of.
So now let's pivot and let's talk about audiovisual speech recognition, and let's also talk about the image to text work. So recently lots of work came out that said, hey, here's an image and here's text that sort of captions that image. Let's take an encoder-decoder model and generate captions, generate text for images. So if we have that in a how-to video, we should be able to use the video information as well and use it to improve speech recognition. So there's been a lot of work on audiovisual speech recognition already. Most famously extract lip regions and extract information from it, fuse it with the with the standard acoustic model, and it was shown to help, but it's very brittle. The audio and the video stream need to be synchronized. If the relative weighting between them changes, you need to estimate the weights. So it's never, my personal take it's never really worked for a practical application, although you can make it work. So in contrast, what we want to do is we want to improve speech recognition by extracting things from the image here and say, well, we know that this person is outside. We know that this person may talk about an aircraft, and use this to improve speech recognition. So we have this tool for doing adaptive training. So the first thing that we tried was, well, can we, from a good part of those videos in our corpus, shows people. So can we extract information about the speaker, the estimated age, the estimated gender, the estimated race? Can we extract that from the image and use it as an additional feature and feed it into our deep neural network? And there is this Face++ API. So for every utterance in our database, we extract a single frame, we extract a single image from it, and feed it into the Face++ database, and we get sort of a feature vector that says this is the estimated age, male, and gender and race of the person, and use it. They are attributes that should be highly correlated with the acoustic characteristics of the speaker. It gives us an 11-dimensional feature vector. Or we also looked at the speaker actions. So the person could be running, the person could be doing certain things that affect the way he speaks. And those were the first two experiments that we did. And, well, we found those speaker attributes and those speaker actions, it just reduces the word error rate just slightly, 0.6%, 0.5% relative. So the idea that we can extract speaker information not from the audio signal, but from the video signal, it does work, but probably those features are just too noisy. There just isn't enough information to really adapt.
Always seem to be showing improvements, but I would expect that if you somehow screw up this additional information to the liberation, right? Sort of say that you are feeding him the wrong ages and wrong genders.
Right.
You could do it, right?
Yeah.
Do you think you would get worse results? Would it go basically other way around, these numbers?
We don't have ground truth for this, which, I mean, the really nice thing would have been, can we show that if we feed in the ground truth, this works better?
No, other way around.
And
I'm also suggesting
that
it works worse if you give the wrong information.
We haven't tried that.
When you say wrong, you think you give it something impertinent, like the color of the shirt.
Opposite actually, literally opposite. You know, it's a male, you give the female or something like that. You know, because you have a number of things you could do, right?
Yeah.
You say he's 50 years old, I say he's 15 years old, or 7
Yeah.
years old.
Yeah.
See what happens.
Yeah. Well, if on those things, here you could interpret it.
Because they would support you if you get worse. But if you get still better, then
that's a good.
Scratch my head, right?
Yeah, the language model.
There's a language model somewhere. And so those things there are probably having an impact on it.
That's what I'm going to talk about last. So we can adapt the language model.
So we're going to get something to be doing by how much your language model. Okay, anyway, sorry, I didn't mean to.
Never mind. Okay. So our interpretation of these results is that, okay, it's possible, but this doesn't work well. So we need to look at other features that help, that work better. But you're right, it's a good point that we should, if this doesn't work well, but we know we can fake it, we should see if it gets worse. And that's a good idea. Now the next thing that we did was, well, instead of extracting those features, we can also we can get more information about it. And there are all those ImageNet, AlexNet, those semantic indexing features that tell us, well, what objects are in the image. And it could be that here it gives us a high probability for a mushroom. It gives us things like jelly fungus. So we get a distribution of objects that we can see. And again, that's just and we can treat it as an embedding. We don't need the 1,000 classes for object features that we can detect, and we don't necessarily need the 205 classes of scenes, place features that we can extract using different feature detectors. But we can either train a bottleneck layer in those detectors, or we can take the output, do PCA, and treat the output of this network as an embedding of what can be seen in the image, and take this output and feed it into the acoustic model and adapt our recognizers. And indeed, as we do this, we can see that simply concatenating 100-dimensional object features and 100-dimensional place features gives us very small but somewhat consistent improvements, and doing the adaptive training again gives us a better improvement, 1% absolute. And of course now the question is, if each of those individually helps a little bit, well, what happens when we put all of them together? And we can see by performing adaptive training on all those features together, so now we have a 261-dimensional feature vector that contains the objects that we can see, the places that we can see, the scenes, and those speaker features. We get a 2% absolute improvement, 8% relative. So we can, and that sort of is slightly better than doing the I-vector adaptation again. So by extracting those features, we can indeed get information that helps to improve speech recognition by learning something about the scene, saying, is it indoor, is it outdoor, is it in an office, is it a male speaker maybe talking, and of course, why does this work, or what's actually going on? So we labeled our test set in terms of, is this a typical indoor video with probably clean audio, or is this an outdoor video where we have lots of noises in the background? And we can see this is on indoor videos we're only going from 22.1% to 21.7%. So if you're in an office or if you're in a clean room, we're not helping the speech recognition much in this case. But if we're outdoor and we are, say, here in a ballpark and we see typical ballpark noises, or we are on a train, those are individual examples of videos where we're going from 34% to 28% with error rate, where we're going from 44% to 38%, and even on average on outdoor videos we're going from 27% to 25%. So we're seeing a bigger improvement on videos where you would expect to see an improvement on those types of videos, because the acoustic conditions are more challenging and are more variable than in typical indoor videos. So it does seem to make sense. Although the interesting experiment would be to feed misleading or random information and see what happens there.
Yeah, this is my feeling. Sometimes I tell to my students, we always have a hypothesis. Whatever we do, things do better. But we can always set up experiments and we set it up and we say, if we are right, things will be worse.
Right.
And I think in this case it's very tempting. And
Yeah.
I mean, because, sometimes I thinking, is it because there is some more information, but it doesn't really matter what you give it, maybe random, or actually in this case we can do literally opposite, or wrong.
Yeah. Well, typically outdoor videos, you have more activity. So the person, typical outdoor videos, the person is on a train, so we have lots of background noise, or the topics that people will typically do in an outdoor video is, I'm going to explain you how to play soccer, how to do a ball game. Those things just seem to be a lot harder, and I would say that the variability outdoor is much bigger than indoor, even though maybe reverberation may not be a problem. I think we did some more analysis, and by and large, all the outdoor videos have higher word error rates. Although, I mean, there are specific cases of indoor videos, like here, for example, the cooking video. We do have a lot of videos about how to cook, and that seems to be a specific environment where there's the pan, the frying pan, or the microwave is on, and we're seeing a huge improvement on this particular video, but on average on the indoor videos we don't see that much improvement. I don't have the
ground truth.
No, we don't have no ground truth, but we have a 4-hour test set. We tried to manually label the activities and say, oh, this is typical indoor, this is typical outdoor. For most of them, we know what category they belong to, and we're trying to make sense of the results. But it's not. I think we would probably still need more than 4 hours of test data to be able to get statistically significant results and say clearly this is what's going on. But yeah, let's do an IARPA project on it, and then we can do those types of.
Just to sort of suggest that Andreas' question may not be as valid as first thought. If you look at the video on the bottom left, I don't know whether it's a lapel microphone on the guy, but even when it's outdoor, it doesn't necessarily mean the microphone is far away. Right? So you have no idea where the microphone is at.
Then is the engine of the plane on?
Yeah.
Then you should have plane, empty, and then we'll know that forget about getting the map, the speech.
Yeah. So I'm.
How much material do you have?
Yeah, I know. We are unsure.
Yeah. Well, this is so. I'm closing. This is the. I should have reduced the introduction more, but. So the obvious next question now is, if I know that this person is in the kitchen, and wouldn't really be the language model the thing that I wanna adapt, and so we're using, and now that there is context-aware language modeling is starting to become a thing. Even machine translation is starting to become context-aware. There was a workshop this summer saying, hey, when you translate those captions of images, can you become better if you have the image that this text describes? So if I have the English sentence, a brown dog is running after the black dog, and I know that this is a caption of this image, and now I do neural machine translation from English into German, and I have this as extra information, does it help? And it does help a little bit. And so we want to do the same thing in speech recognition. So obviously what we're going to do is we're going to use a recurrent neural network language model and train it and use those same features as extra inputs that we put next to our words. And if we train a baseline neural network language model, we can see that it trains, but it starts to saturate. But if we train our video language model, it really leads to nice reductions in perplexity. And of course, now when we are we use our baseline system to rescore 30 best lists that we generated with our 23.4% word error rate system. We get Oracle word error rate of our 30 best lists of 15.6%. So there is really headroom, and by rescoring the language model with the LSTM language model, the adapted LSTM language model, we get a word error rate of 22.6%. It's simply rescoring it with the neural network language model doesn't give us a significant improvement at all. So there is a small but consistent improvement. I don't think this is the end of the line there, but when we started this work before the summer, we didn't know the outcome of this WMT workshop on context-aware machine translation. Their conclusion was that, yeah, the neural information helps a little bit. And so this is consistent with what we found over the summer, that having the image information available in the language model, it does help a little bit. We did do more analysis, and we said the acoustic model adaptation, it only improves 55 videos in the test set out of 156, but those it improves quite dramatically, and those tend to be the noisy, the outdoor ones, while the language model adaptation improves the results across the board. So there's only 126 videos that improve out of 156, and they all improve by small amounts. So it's sort of consistent in the sense that the language model adaptation, we have topic information for everything, and by putting the topic into the language model, it helps a little bit, and we have difficult, noisy videos that we can specifically target with extracting information about the environment from the image. So to conclude, we have this general approach to do adaptation with DNNs. It doesn't really matter what we feed in as an adaptation vector. It can be I-vectors, but it can be speaker microphone distance, or it can be information extracted from the image. In all cases, we are seeing improvements. We are seeing reasonable improvements for the acoustic model adaptation. I don't think we've seen the end of the line for the language model adaptation, but I think it's really a neural network acoustic model, neural network language models, or end-to-end systems really should give us a great platform to work on this type of thing when we're not just generating captions for images, and we're amazed that it can be done at all, but we really should try to incorporate this extra context information into speech recognition by knowing what is the objects, what are the scenes that people talk about, and use it to improve the analysis of YouTube videos or consumer-generated content, which is really one of the things where we still have really high word error rates. And if you also think about low resource languages, if you had not just English data, but if you had not speech in a low resource language, but video in a low resource language, this context information might be even more worthwhile than it and more useful than it is in English today. So, right, I spoke for just about under 60 minutes. We started a bit late.
If there is anybody who really has some burning question like Karen, for instance, I think that we should allow for a few questions. We still have a few minutes.
So I wanted to ask about the specifics of speaker adaptive training. We're doing tricks to make it work. For example, you say there's two phases first you train a speaker and then the system. How far do you have to train it before you switch off and use some other adaptation network?
We really just, this seems pretty robust, so we trained the model just like we normally train a model, and then we trained the adaptation model, and then we restarted the training of the main model. It doesn't seem to be very, very sensitive.
Like ResNet does everything once.
Right. Yeah, I'm not saying that we're doing the same as ResNet, but when it came out and we read about it, we were like, oh yeah, that's really also what we're trying to do to remove this residual a little bit. And you could, of course, think about ways to train them together, but we haven't done that. So for this work, the point is whatever you feed into your neural network, it doesn't matter what it is, as long as it's useful. And I agree that we should do the
Useless things.
yes.
Harmful things. Okay. Thank you very much. We had plenty of questions. Means there was very good talk, I think.
Good, thank you.